When my heart was a rock, I knew it was gold.
Someone could change it, like an alchemist of old.
You came along, gave my heart birth.
Now our love's more precious than anything on earth. Transformation, you're changing me with fire. Transformation, your flame is my desire. Transformation.
Hey, Simone, how's your little brother doing? Is he still in the hospital?
No, the twerp's back home. He's all better.
Already? I thought he had pneumonia.
He did, but they gave him penicillin and it took care of it. Poof, like that.
Help!
Hey, Billy.
Hey, Billy. Starving. Desperately need something to eat.
I wish they had a shot that worked like that on zits.
Oh, don't worry. I can't see them.
Hey, that's a cool bracelet.
Thanks.
Did you make that one too?
Yep.
Kid's talented.
Aha! Ha 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 ha.
Oh, there's a fungus among us.
What's the matter? Afraid of a little mold, Scarecrow?
It won't hurt you.
It's nasty.
Oh, I wouldn't laugh, Simone. Your yogurt is full of all those little creepy crawlies too.
Yogurt? You're joking.
Oh, come on, you remember? They're everywhere. Trillions and trillions of microbes all around us, even right on your skin.
Thanks.
You're sly, you're small, but I've got my eye on you.
Hey, yo. Yeah, and double cheese. That's very important. Don't forget it. How soon can you get it here? Thank you. Hey, I like that. Let's try something with that. Am I plugged in?
You're all set.
Thanks. Okay, count it off.
Microbes are the oldest form of life on the Earth. For over 3 billion years, they found a paradise on Earth. Microbes were hanging on to the first amphibians when they crawled out onto the land.
Boy, is this dry.
They watched the dinosaurs come and go.
I'd give these guys 250 million years, tops.
Microbes live where it's freezing cold
Ski City!
and boiling hot.
Let's hit the sauna.
And for microbes, people are just the latest great hangout.
Give me some skin.
They're on our skin, in our mouths, in our throats, and even in our intestines.
I love this dude.
They can cause disease, and they help make medicines, treat cancer, and produce cheese, yogurt, bread, wine, and gas. They can be used for cleaning up oil spills, and even mining minerals.
Huh?
The problem we're working on here is how to use bacteria to remove the manganese from an ore. What we're doing is trying to identify types of bacteria that can actually release manganese from our ore into solution. Wait a minute. I understand that bacteria is in so many different things. I mean, bacteria is in the food that I eat, bacteria is on my skin. But I don't understand how you could possibly use bacteria to remove something from the earth? Right. There's a whole lot of different types of bacteria in the world. And what we're trying to do is we're using the technology that was developed with copper mining. There actually is a type of bacteria that can attach to copper sulfide particles and eat the sulfide away from the copper, and the copper goes into solution and can actually be washed out of a heap, so you can recover the copper from an ore. And we're using the same idea on our manganese here.
Wait, what is manganese?
Manganese is it's an element, and it's used in different kinds of steels, and it's used in paints, it's used in fertilizers, and it's also used in batteries.
So this looks like a really big mess. I don't understand what it is.
In our columns here, we have a manganese ore. You know, since humans need to eat, well, so do bacteria. So what we're doing is we're pumping in a nutrient solution. And what the nutrient is in there, it's just like an everyday molasses. We put the molasses in water, and then we percolate it down through the columns.
Why do you use molasses?
Molasses is a good form of carbon, and that's what these type of bacteria eat, is carbon.
I know what carbon is. Carbon's a very small, simple molecule, right?
Right, it's actually an element, the same as like manganese or even copper.
Are you guys looking for something in particular in the bacteria? I mean,
what we've done so far is we decided that whatever bacteria in the ore would probably be the best bacteria to use because they've been associated with the ore from day one. So instead of using some pure strain from somewhere else, we're just going to use whatever's in the ore. So what we do is once we get some solution percolating through here, we assume that with the carbon that we put in there, there's going to be bacteria growing. So we take a sample from this, and we plate it out on these plates, and this is what we get. See all the different colonies on there?
Ew, that's really gross.
Colonies. See all those different colors and different sizes?
Yeah.
Those all represent different bacteria.
Yeah, there's about 1, 2, 3, 4, maybe 5 different colors.
You can see there's some white ones that look large and some that are just like little pinpoints.
Right.
Those are even different types of bacteria.
So this is actually bacteria multiplying and...
Right, exactly. Each the bacteria, they actually produce or reproduce by, it's called fission. And fission is just
It's a cell.
Right, cell divides, right. And there's even some cells that split every half hour. So by the end of 15 hours, you have over 1 trillion cells.
Trillions of bacteria? You mean millions of bacteria?
No, trillions.
Trillions of bacteria in 15 minutes?
No, 15 hours.
15 hours?
Yeah, they split every 30 minutes.
That's like a population explosion.
Right.
I mean, it's a good thing that we know how to get rid of bacteria, otherwise I think they'd probably take over the entire planet.
Right, but nature has its way of taking care of things like that.
So have you figured out which bacteria it is that works on the manganese?
Not yet. We've identified, or actually isolated, 30 different strains of bacteria, and actually some fungi and some yeasts also.
30?
30. That's how many we've identified so far.
Okay, I think I'm getting the hang of this. Each color and size on this petri dish represents a different type of one of the 30 types of bacteria that you're finding.
Right, exactly.
So the next step would be to try and isolate each one and grow it by itself somewhere else to see how it affects the manganese and separates it from the ore.
Right, so what we could do here, say for instance we want to isolate this orange one from all the others that we see here. We take the sterile inoculating loop and just kind of drag it across the surface of that particular strain, and then take a fresh petri dish and then just start spreading it out on the surface of this dish. And you rotate the dish to spread it out further, so when it does start growing, you'll be able to get pinpointed colonies more, so you'll be able to tell if it was an actual pure strain. See, now this one, you can't even see the growth, right?
No, I just see some scratches.
All right, that's where I drug the loop across. And what happens after a couple days, you'll start getting plates that look like this one, for instance. This is one of the white colonies that we streaked. And what you look for here is to make sure that everything on this plate is the same. You make sure there's no other colors of colonies, other different shapes or sizes.
There aren't. There's nothing else on here.
Right, so we can pretty much be sure that this is one of our pure cultures.
Great. Can I open this?
Sure. Go ahead and smell it. You can. All the bacteria have a unique smell.
Oh, gross!
Okay, Simone, I have this focused in on some bacteria now.
Okay, I see them. Some of them seem to be moving really fast, and some of them seem to be staying in place.
Ones that are spinning or going against the flow of the solution, those are actually modal. Okay, so our next step then is we're going to take one of those pure colonies and see if it's actually able to leach the manganese.
Leach the manganese.
That means taking it from its solid form and putting it into a liquid.
Okay.
Okay, so what we've done is we've taken a different type of plate and put this manganese dioxide overlay on it. Then we inoculate one of the types of bacteria onto it, and as it grows, what we're going to be looking for is a clearing zone around that, because that means it's taking the manganese and it's utilizing it and actually putting it into solution.
So you can actually see it getting thinner.
Right, so that's what we see here in these photographs. What you see here is what the plate looks like before we inoculate the colony. All the little black particles you see are the manganese.
Right. I see that, and in the second picture, it looks like they get lighter and thinner. And this must be the third picture right here. They're even thinner in the third picture.
Right. As time goes on, the manganese particles are getting smaller and smaller and finally starting to disappear. So that means that colony is actually going to solubilize manganese. So that's one of the bacteria that we're going to definitely identify and utilize in our future tests.
So even though you don't know how many of the bacteria work, you know that this one is definitely going to help you somewhere along the way.
Right. This is definitely one of the ones that we want to work with.
So what do you like best about your work? I mean, what's your favorite part of your job?
I think my favorite part is that it's always challenging. There's always a new problem to be solved. You know, even if you solve one problem today, tomorrow there'll be a whole nother problem for you.
That's great. You know, Debbie, I've been thinking about the 30 bacteria from before. I'm confused. I mean, what if it's not just one kind of bacteria that's separating the manganese? What if it's a different combination than you ever thought of? I mean, 4 bacteria working with 6 bacteria at different times. What do you do?
That's a good question, and more than likely it will be more than just one bacteria. That's what we're going to have to figure out. We're going to have to take all the different bacteria we found so far and put them together in different combinations.
Sounds like it's complicated.
It is complicated, but it's challenging, and that's what makes the job fun.
The problem that the bacteria are helping us solve is to recover the copper in this low-grade ore. This copper wouldn't have been recoverable by other means.
Wow. So, is there actually bacteria in the water that you're spraying right now?
Well, actually, the bacteria live out within the rock itself and just kind of feed on the elements that are within that rock.
You mean the bacteria are actually a natural part of this environment?
They sure are. This is their home.
That's pretty lucky.
You know, the bacteria will thrive on the sulfur and iron that the rock contains, and as they're doing that, they'll release the copper and allow it to go into the water.
Are you doing anything for the bacteria? I mean, are you feeding it with something like glucose or molasses or something like that?
No, all we have to do is supply the bacteria with a slightly acidic environment. The way we do that is to apply this water that contains a little bit of acid, and the bacteria just kind of cook along on their own.
Well, how come the water's green? I mean, does that mean that there's actually copper in the water right now?
Sure does. The water that you see out here has traces of copper and a little bit of iron and some other things that the bacteria have released from the rock.
Are you trying to get the other things out as well as the copper, or are you just going to leave all the other stuff in?
We're going to leave all the other stuff in and recover just the copper.
This is great! I don't believe it. I've never seen a green river before.
This is the water that we sprinkle up above on the top of these heaps. As that water percolates through this rock, that acid that we supplied the bacteria will allow them to go ahead and take this copper into solution. That allows the water to go ahead and wash it out of the rock. We'll collect it in these canyons, channel it into these stream beds, and let it flow on down to these sumps where we'll collect it and send it on for further processing.
So how much copper is there in this water?
Well, at this point, this water contains about 2.5 grams per liter of copper sulfate.
So is this the end of the whole process?
From here, this water will be collected and we'll pump it up for further treatment where we're going to purify it and make pure copper out of it.
This place is huge!
After we collect the solutions in the sump down below that we saw, we'll pump that water up to a process called solvent extraction. We'll purify it and we'll concentrate it into what's called an electrolyte solution. The electrolyte solution will be pumped up to this, it's called a tank house. The process involved there is winning that copper from solution and actually turning it into metallic copper. Take it out of the water form and turn it into a solid copper metallic product. We're applying an electrical current to this concentrated, purified copper solution.
So, I know a little bit about electricity. So that copper must have a positive charge and there must be a negative charge somewhere else, and it must be somehow attracting the copper.
And we're supplying a direct current to these cells. The electricity will actually give that little copper atom a negatively charged electron. When it bonds with that positively charged copper atom, it becomes metallic copper. This is it. This is the finished copper product. This is 99.99% pure copper. The copper that you see here was taken out of solution. We'll give it a couple of electrons and metallic copper. It's ready to turn into wire or whatever else we want to make out of it.
I can't believe you're getting this
from the blue liquid at the solvent extraction plant?
All of these solutions will be returned back to solvent extraction, where they're continually recycled. The water that we remove that copper from initially is recycled and taken out back out to those leach heaps where it starts the whole process over again.
Sounds
so basically there's no losses, no pollution problem.
Conservation. Yeah.
You're small, you're sly. I've got my eye on you. You're cool, you're smart. You've been there from the very start. You know you can all do things, but you can't do more. You travel all over the world to those distant shores. You're clean, don't know where to begin with you. You're small, you're sly, but I got my eye on you. You're cool, you're smart. You've been there from the very start.
Hey, where's Simone?
That was really nice.
Hey, that's my pizza!
It's really good.
But Simone, cheese has all sorts of bacteria in it.
I can live with that. Bye.